Right, thank you. Great. So yesterday we were looking at the co-compactness of the action of gamma on the set K rho hats, right? Which is in the end going to, and this is what we're going to do today, prove that this is actually the non-wandering set when you go to the quotient by gamma. There was, as I said, a slight mistake in my notes that I fixed. I just haven't uploaded the new version yet, but that will be done shortly. There was some Z in some bundle that was not the bundle that I pretended it to be, but you can fix it either by saying that this bundle is also dilating for this flow, or you can change the bundle and check that this bundle also works. So in the end, it's a simpler proof in the notes now. Okay, so now we had this action on K rho hat that is properly discontinuous, and what we call the refraction flow is the quotient flow phi t on K rho, which is the quotient by K rho hat. And we did this whole conversation about Gromov flows and coarse Gromov flows. Something that should be said is now we won't need any abstract Gromov flow anymore because this is a Gromov flow. Right, and Gromov flows were defined in terms of having in the cover, so in here that would be in the K rho hat, that the flow lines would have limits when t go to plus and minus infinity, and that these would give a homomorphism between the orbit space of the flow on K rho hat and distinct pairs in the boundary of gamma. And to have this, actually, this homomorphism will be quite natural given this description. So more precisely, given some V alpha in K rho hat, if V is psi of some eta plus and alpha is psi star of some eta minus, well, then the limit as t goes to plus infinity of the flow. So here, maybe I'll write there, just to remember that when we're working inside this space L, this flow phi t is just multiplying v by e to the t and alpha by e to the minus t. And we defined these limits for gamma flows as being in the boundary of gamma. So then the point in the boundary of gamma that you'll get for the limit as t goes to plus infinity is just the point eta plus that corresponds to v, and same for minus infinity. You'll get eta minus. Yeah, it gives a proof of the existence of Gromov flows for hyperbolic groups admitting Anosov representations.
The proof of compactness uses coarse.
Yeah, you can do it with just a core Gromov flow, and that's easy to find. But yeah, but also like the Gromov flow isn't that complicated of an object. Like Gromov's construction is, it's just that it's details you have to work out. Yeah. And really, actually, it's somehow doing the same proof in this precise context, right? Because the proof of Gromov is just that you might have several geodesics with the same endpoints, and you collapse them all to the same point, and this is exactly to the same line, and this is exactly what the map f hat is doing. It's just first considering the endpoints and then trying to figure out some point you want to map to on this line. And from there, what you find is that if you want to study all these bundles that we have defined with this flow k on k rho now, instead of an abstract Gromov flow, then all the sections of bundles that you will define will become very tautological. Right? So for example, we had, so recall the section sigma plus. There was a section on, so now that would be on k rho, which is a Gromov flow, to this bundle where with fiber the projective space, and this thing was defined as being the orbit under gamma. So this was defined as a quotient by gamma of k rho hat times the projective space. So it should be the orbit of some point in k rho hat and some point in projective space, and your point in k rho hat will just be, well, the point you started with, v alpha, and the point in projective space will be v, right? Because it is psi of the limit as t goes to plus infinity of v alpha, so it is psi of eta plus, so that's just v. Right? And also for the section sigma minus, you would have the same thing. Where the orbit of v alpha is just sent to the orbit of v alpha and alpha. So these things become much more natural and much easier to work with because of these tautological properties. Okay, so that's for the end of the second part, which was proving this proper discontinuity. Now we can move to the third part, which is the dynamics of the quotient flow. Right, so now we have well, for the whole section, I'll just be fixing some hyperbolic group and some Anosov representations of rho. And we'll assume it to be torsion free so that m rho is actually a manifold. And so k rho, as above, is just the quotient of k rho hat. And so now we have a flow phi t rho that is the quotient flow defined on the whole quotient manifold m rho, and this preserves the compact subset k rho. So we're already in the setting of having a smooth flow, even a real analytic flow, on a real analytic manifold m rho, preserving a compact subset k rho. And what we're going to try to figure out is that this flow is an axiom A flow with non-wandering set k rho. Right, so that's the next result we're going to be talking about. This is an axiom A flow. And k rho is exactly the non-wandering set. Okay, so for axiom A, I'll just give definitions. I'll recall the definitions as they come, because there were several things. Essentially, there's a topological dynamics component, which is, for us, this statement that k rho is the non-wandering set. and it will also have to be the closure of periodic points. And then there's this hyperbolic component saying that the tangent bundle of M rho will have a splitting into contracted and dilated vectors. Okay. So let's start with the topological dynamics. So what we want to understand here is why k rho is exactly this non-boundary set, and why it's equal to the closure of periodic points. And also one last thing, which is that the flow restricted to k rho is transitive, or topologically transitive. I think you've seen this notion in one of Simeon's lectures. That just means that, or maybe in the exercises, I can't remember. But it means that that it has a dense orbit here, right? Yeah. And this, in the study of, in dynamics in general, is an important notion, but especially in the study of axiom A flows. You know that when you're studying this non-wandering set, in general, it consists of several what we call basic sets. And you may have to study this thing by decompose it into several pieces. And this topological transitivity is telling you that it only has one basic set, so really you're going to be studying this non-wandering set as a whole and not have to bother about cutting it into pieces. Right, so let's start with periodic points and trying to understand what periodic points are, because that's the easiest part, right? So that would be a lemma. Let's say you have x in M rho, a periodic point, so its flow comes back to x for some positive time t, and you choose some lift v alpha. Well, then what will happen is that there exists some element gamma such that the v is equal to psi of the attracting fig points gamma plus. Alpha is psi star of gamma minus, and t is lambda 1 over rho of gamma. Right, so t will be the largest eigenvalue, the log of largest eigenvalue. And actually, this is an equivalence, I should say. How should I say it? Just remove this part and say that phi t of x equal x is equivalent to this. Okay, because this will be a characterization of periodic points for a quotient flow. Right. So just to understand the mechanism behind this, so phi t of x equals x means that on the quotient, that's on the quotient, and when you lift to v alpha, it means that phi t, so it's phi t rho, by the way, phi t on L of v alpha is rho of some L is in the orbit of v alpha, right? It projects to the same point. It just means that it's in the same orbit, right? So for some gamma. Right, and so now you'll have rho of gamma v, rho of gamma acting on alpha is exponential t v, exponential minus t alpha. So here you'll want to say that, you'll see already that it means that v is an eigenvector for rho of gamma, right? For the eigenvalue exponential t. That's what it looks like, at least. It's not necessarily exactly the case. It could be plus or minus exponential t, because there's this whole projective class thing going on here, right? That you have to be slightly careful. And same, alpha is an eigenvalue of rho of gamma for plus or minus exponential minus t. Yeah, it's trying to figure out what I want to call rho of gamma here. Sorry?
Perhaps you want like non-zero number times e to the t?
Perhaps I want what, sorry?
Why plus minus?
The plus minus here?
Or like not the scale, not the plus the scale.
Why not a scale? Because when you're pairing the linear form and the vector on each side, you'll find that they have the same value. And that tells you that you'll have the same scaling, essentially. Yeah. Right. And so now what you have to make sure of is that t will be the largest eigenvalue of rho of gamma. And that's where you use the fact that you use the definition of m rho hat, right? M rho hat has been defined exactly to just get rid of all these other eigenvalues. So. And once you'll have this, automatically v is an eigenvector for this, though it means that by definition or by the dynamics preserving condition, the class of v will be psi of a gamma plus, and same for alpha with psi star of gamma minus. Right, so what you do for this is you consider psi star of gamma plus and write this as the class of some element beta. Now gamma plus is an element of the boundary of gamma, so you're going to be using this definition of m rho hat. So you know that either v is transverse to psi star of gamma plus, or psi of gamma plus is transverse to alpha. Yeah. And if you're in the, say, the first case, psi star of gamma plus is transverse to v. This means that, beta applied to the vector v is non-zero. Okay, so that's the definition of transversality. And now you're just going to apply rho of gamma to all of this, and see that, no, because this is rho of gamma acting on beta times rho of gamma acting on v. And because beta is in psi star of gamma plus, this will mean that it's an eigenvector, but it's the psi star, an eigen linear form, but it's the psi star. So the eigenvalue is minus lambda d here. It's the opposite of the, so there are always plus or minuses. So we've taken the inverse of gamma essentially here, right? Because gamma plus is the gamma minus of gamma inverse. So, and here you have your plus or minus exponential t v. Right. So if you have beta of v, which is equal to this thing, you get beta of v, and if beta of v is non-zero, this means that that thing in the exponential has to be 0, right? But this is a problem. This is a problem because t was positive, that was just an assumption, and because your matrix rho of gamma is in SL of v, the smallest, this lambda d, has to be well, it cannot be negative. Oh, sorry, lambda d cannot be positive, so minus lambda d cannot be negative. So this is absurd, right? Right, so instead what you must have is the other, let me pick some other color here. So what you must have instead is the other transversality. Is transverse to alpha, okay. But now psi of gamma plus, we don't have to think with inverses anymore. This is just the eigendirection corresponding to the largest eigenvalue. So if you write psi of gamma plus is choose some vector w in there spanning it, right? So you'll have rho of gamma w is plus or minus exponential lambda 1 times w. And here you have alpha of w, which is non-zero because of transversality, and you do the same thing. You apply rho of gamma on each side. And you'll get eventually some plus or minuses that will have to compensate in the end. And you'll have lambda 1 of rho of gamma minus t when you look at this, okay? So the thing in the exponential has to be 0, and you get your formula for the eigenvalue. But now that this is your eigenvalue, you know that your v and alphas were already in these eigenspaces. So this also, because they have dimension 1, this in turn will imply that v is psi of gamma plus and alpha is psi star of gamma minus. Yep. All right, so this gives you a description of all the periodic points in this quotient. The periodic points of phi rho will be exactly sorry, I'll have to write something bigger. When you go to m rho hat, a periodic point will lift to something which is v. So there exists some gamma in your group such that v is a psi of gamma plus, and alpha is psi star of gamma minus. Yeah. So now when you want to understand the closure of these periodic points, well, that would be the quotient of these v alphas for which the V psi of something and alpha psi of something else, which are in the closure of pairs of attracting, repelling points of elements in the group. And it happens that this is dense. So the set of pairs gamma plus, gamma minus, such that for elements gamma here, this is its closure is pairs in the boundary. Okay. So from there, you already know this already implies that the closure of periodic points of phi rho will be equal to k rho. Yeah. Okay, so that's it for the periodic points. Now you just have to make sure that this is also the non-wandering set. And I won't do the detailed proof for this one. I'll just give the main lemma that tells you how it works, and it's pretty similar to some to either this argument here or some other that we had for the proof of proper discontinuity. So the lemma is that if you have, well, sequences like you would have for non-wandering points, so let's say you have some xk converging to some x in the quotient m rho, some sequence tk going to plus infinity, and such that phi tk rho of xk converges, but maybe to some other point y. It's a slightly more general situation. It's more like trapped orbits, essentially. Now, if you write if you write x as the class of some v alpha and y as the class of some w and beta, then you'll automatically have that between VL and alpha, one of them is in the limit set, so its class will be in psi of something, and the other one will have the same property for y, and I never remember which, so I really need my notes for this one. Then it is V that is in psi. So V is psi of something, and beta is psi star of something too. Right, so this is really understanding the this same kind of mechanism for lifts, but now you have to be slightly more careful because you have a whole sequence. You have to choose your lifts so that the lifts of the xk converge to the lifts of x, but then the lifts of these phi t don't necessarily converge to the lift of y, so you have to take rescalings and make sure to what happens to these rescalings. Yes?
What are we trying to do now?
Yeah, so I was just stating this lemma here, right? This is telling you that if you have some non-wandering,
Why do we want to do this lemma?
because the consequence of this is that the non-wandering set is equal to k rho. No. Yeah, no, it's not the definition.
What was the definition?
The definition was that it's an x such that there exists a sequence xk and a sequence tk with this but converging to the same x. That's the definition of the non-wandering set.
All the x such that we can find the sequence.
Yeah.
Okay.
And
Now the lemma makes more sense.
This is actually slightly more general. To get just a non-wandering set, you could put x equal to y. But then, because of stuff that we're applying, we also need to make sure that it's equal to some other thing called a trap set. And so here you need to have, it's also going to tell you what the stable manifold of the non-wandering set is and what this unstable manifold is.
And you said the non-wandering set is always closed, right?
Yes.
And so this is always a subset, the closure of the periodic orbits.
Yeah, what is always true from the closure of periodic orbits is always included in the non-wandering set. But the reverse inclusion is not automatic. You have to prove it. But it will come from this. Because this directly gives you the equality between k rho and the non-wandering set. Well, directly, no. It directly gives you the inclusion that the non-wandering set is included in k rho, let's say. But now that you also know that k rho is equal to closure of periodic points, that gives you the final word. All right, so now we're going to move to hyperbolicity, unless there are also some questions about the topological dynamics. Okay, so now what we have to do is find this decomposition of the tangent bundle to the manifold M rho, but only over points in K rho as some unstable direction E0, which is just the direction spanned by the flow, and some stable direction, right? So this dilated, this contracted. And in the general theory of even Anosov flows, and even more for axiom A flows, what you will find is that these EU, E0, ES, they will be tangent to some nice submanifolds, which are these stable and unstable manifolds from Simeon's lectures. And these stable and stable and unstable manifolds will be some very regular submanifolds, but the foliations coming from them will not be, right? Meaning that these EU and ES will only be continuous vector subbundles of the tangent bundle and nothing more in general. Well, Hölder, but nothing better in this whole generality of axiom A flows. What we're going to have here in this situation, because everything comes from a homogeneous flow on a homogeneous space, they will be very smooth. They will be analytic because they come from the group structure. And this will tell us in the end that we not just have an axiom A flow, we have a very nice axiom A flow, and we have more properties because of this. Okay. So to understand this splitting, actually this splitting is going to happen on the whole manifold M rho, not just on K rho. It's just that the contraction and dilation will only make sense on a compact subset, as we already have said at some point. So we're just going to be looking at the, instead of M rho, we're going to go back to our space L, which, as a reminder, was projectivizations of pairs in V plus V star with a positive pairing, and try to understand the tangent spaces to this, right, and then take the quotient. This is a tangent space to a projective space. It's much easier if you work in a double cover here, which will be the sphere, essentially, right? So if you're working with this in the sphere, tangent spaces are just the orthogonal to your direction. So we'll consider some L sub 1, which is now pairs V alpha but not projectivized, for which the pairing alpha V is equal to 1. Right. And if you take the projection to L, this will be just a 2-to-1 cover. And you also have the same flow happening on L1, which is multiplying V by exponential t, alpha by exponential minus t. It preserves this pairing equal to 1. Right. And why is this easier? Well, if you were to work out the tangent space at some V alpha of L1, you don't need any identifications or anything like this. You just say that this is it's a submanifold of V plus V star. So the tangent spaces are just linear subspaces of V plus V star. And you should be able to differentiate the function mapping V on alpha to alpha of V. So your condition is that alpha of W plus beta of V is equal to 0. That's your orthogonality condition. Okay. And this has some pretty simple subbundles in there. We can define a first one, which is the direction spanned by the flow. Maybe I'll put some ones in there to say that these are the bundles on E1, on L1, sorry. And actually, there's a very simple formula, right, for the fiber of this. I think you can also differentiate, where is it? Mapping t to exponential t v and exponential minus t alpha. And this will just be v minus alpha. And this is in the tangent space. Yeah?
When you pass to Grassmannians, I mean, over Anosov, what is the analog of L1?
There's not necessarily an analog in general.
Okay.
Yeah, that's just
yeah, it's a trick in this case.
Yeah, it's really because now we're really using the homogeneous structure, essentially. Okay. So everything we're going to be doing now is very specific to this case. Yeah. I mean, it's the very irregularity of stable and unstable distributions in general that tells you that something irregular cannot have a nice formula, right? Otherwise, it would be regular. So, I mean, that's how you prove that a function is smooth in any calculus exercise, right? You just say, well, it's a nice formula. These are functions that I've already seen. I know that they're smooth because I was told so. Okay. Now we're going to define what will be the unstable direction. It has to be something dilated, right? And there's an exponential t here in front of v. So it sounds quite reasonable to say that this should be the sets of, so for the fiber over v alpha, it should just contain the w and not the beta. And now your condition for being in the tangent space is just that alpha of w is 0. So this is essentially, I mean, it's clearly isomorphic to the kernel of alpha. And after this, you'll be looking for something stable. For something stable, multiplication by exponential minus t seems to be a reasonable choice. And so you'll have 0 in beta, for which beta of v is 0. If you wanted to write it as you could write it as an orthogonal of the vector v in the dual space, or as some kernel of the evaluation form at v. All right, so these give you 3 invariant subbundles of the tangent bundle of L1, this 2-to-1 cover, but they are invariant under the flip map.
Sorry, the kernel of what? The last term?
Evaluation at V.
Okay.
Yeah.
Right, thank you.
Yes, the inclusion of V in the dual of its dual. Right, and so we do have that TL1 is ES1 plus E01 plus EU1. That's also quite clear. And from this, you also get splittings on L. Right, just because it's invariant under everyone that's living there, that's acting on this. They're invariant under the action of SL of V, invariant under this covering transformation, which is sending V alpha to minus V minus alpha, and they're also invariant under the differential of the flow. So this decomposition here of the tangent bundle of L is invariant under SLV and the flow phi TL. And because of this invariance, when you go to a quotient of some open set of L, you'll also keep the same splitting, right? From there, if you want to check that ES is contracted and EU is dilated, you might want to compute the differential of the flow. And that will be an exercise, for example, that on, say, on ES, so if you have some W0, let's work on L1, so that this will be easier. You'll be looking at the differential of the flow on L1 over V alpha applied to W0, but your flow is a very linear thing here, right? So your flow is just exponential minus T, W, and 0. This looks like a very contracting flow. You can do the same for 0 beta and EU. You'll get 0 and exponential T beta. Here's our proof of contraction, right? The answer is no. This is far from being the proof. Yeah. Sorry?
Isn't it 0 beta? When S is the 0 beta,
Yeah. U plus. Thanks. So this looks very dilating then, or contracting in negative time. But this happens to not be enough, and this will be an exercise to understand why this does not work. It has to do with the impossibility of choosing norms that are invariant under SL of V. Contraction and dilation should be for a Riemannian metric on the quotient space. And the Riemannian metric on the quotient space, it lifts to a Riemannian metric invariant under the covering group. And here you cannot find, like this proof works for the hyperbolicity of the geodesic flow of HD, for example, because you can find an invariant Riemannian metric invariant under the isometric group of the unit tangent bundle, which you cannot here. Okay. So
Sorry, this is not enough to prove what?
this formula is not enough to prove contraction or dilation. because contraction and dilation does not look at norms of these vectors in V plus V star. It looks at norms for some Riemannian metric that is invariant under rho of gamma. And there's no simple formula for such a metric. I mean, the existence of such a metric comes from the fact that the action is properly discontinuous. Okay.
So it's not explicit.
Yeah.
You know it exists.
Yeah, so this is not enough to prove contraction dilation on the quotient. Okay, so rather than spending a lot of time now on something that doesn't work, we can look at this in the exercise session later and just tell you what does work instead. Well, what does work is what we were talking about last time. So now we want to work with these tangent spaces on K rho only, right? And we had a contracting flow in our definition of Anosov representations, right? In our definition of Anosov representations, we had this sorry, well, let me start with the easy ones, right? If you look at the flow phi t rho and you differentiated to act on these ES, EU, and E0, and say you let it act on EU, but only over points in K rho, right? So this is a vector bundle over K rho. And what I claimed is that this flow is conjugate to the flow in the definition of Anosov representations. It's conjugate to what we call the vertical flow along this section sigma plus of a suspended flow phi t rho on tangent spaces to projective space. Right, and I just deleted erased the definitions of these sections, of course. Okay, so that was the flow appearing in yesterday's definition. And that, from the definition of Anosov representation, is that this is a dilating flow. Okay, so this is how you prove contraction. I mean, you could also try to work out with these formulas over there and make something that will work, but there's a lot of work to be done. It's not, you'll quickly get to, if you do these computations, you'll quickly see that it has to do with the growth of this gap between lambda 1 and lambda 2. Okay, so I'll try to give some proof of this because it's pretty short anyway. The idea is that, so what was this nasty suspension bundle of some tangent space, right? It has to do with tangent spaces to fibers along some section. It's some suspension bundle. But there's also another simple description that it is itself a suspended bundle, meaning a quotient by gamma of something, and that something will be a pullback bundle, sigma plus hat star tangent bundle of P of V, if I remember the notations, right? So what is this thing here? This would be pairs of something in K rho hat and something in the tangent space, let's call it Z. This is in the tangent space, well, the total, the tangent bundle of P of V, such that V is tangent at the class of V. Right. It's really tangent to sigma plus of V alpha, or sigma plus hat of V alpha, which is this now this tautological section is just V. So we just have to find an isomorphism between this bundle, this pullback bundle, and EU over K rho hat, right, the lifted one. So over K rho hat, this means you'll have in the total space of the bundle, you have your base point V alpha and some vector W, so W0. And you know your base point also has to be V alpha. And now you want to know what vector to put there. What the answer is pretty simple. It's the differential of the projection P, and so P here is just the projection from V plus V star to P of V, right? Well, not on the whole thing, but like on the right, it's mapping to the class of the first factor. You just look at the differential of this at well, I realized, sorry, you don't need V plus V star. Just look at the projection from V minus 0 to its projective space. That's easier. Okay. V of W. Right. And now it's really just a matter of an exercise to check that this is an isomorphism, that it commutes with the flows. And can be annoying, but it's still very possible.
Sorry, what does conjugate mean?
Conjugate means that there is so an isomorphism would be something which is a homomorphism on the total space and linear on fibers, right? And that intertwines the actions. Okay, I'll just, with the 5 minutes that I have left, we'll say a word about the consequences of having an axiom A flow. So that would be 3.3. Right. All right, so maybe something I could add to this proof, or at least to the statement, is that what we're doing here is taking this abstract construction of a suspended flow and this contraction there, and turning it into a derivative of a flow, right? Because the definition with flows of Anosov representation is a definition of contraction and dilation for some flow which is not the derivative of the flow. It's some flow which is parallel transport on some bundle. But now we've turned it into the differential of flow. And the fact that it is something on the differential of the flow means that it will give you behavior of the flow from it, right? So I think I said at some point that there will be some counting estimates, so I'll just give the prime orbit theorem as an example of what you get from this. Right, so when you do counting problems, the kind of thing that you look at is trying to understand in the group conjugacy classes of primitive elements with a bound on lambda 1. Right, so right, so primitive meaning that it's not the power of something else. And now, because of our description of periodic orbits of the flow, this is the same as looking at periodic orbits of our flow on M rho that have a period less than t. Okay, and now there are actual theorems that will tell you, for example, for axiom A flows with just this length here, I think this would be Bowen. That implies that you have an asymptotic for n rho of t of the form exponential h rho t over h rho t for some h rho, which is a positive number, which is the topological entropy of the flow in k rho. But also from this definition, you could write it as some exponential growth of this number, n rho of t. All right, so this was in the context of Anosov representations.
So the axiom A gives you only the equivalent, but if you want error terms,
last or last. Okay, so this asymptotic was obtained by André Samparino, where when he was working with this refraction flow, he didn't have an axiom A flow, and so you can apply Bowen's result straight away. But there was another way to apply Bowen's method, which is that he showed that you have similar Markov codings of this flow, and you can do this for the symbolic flows. Okay. But now the consequences of what I would call having a nice axiom A flow is that you have an exponential error term, right? So there exists some positive c such that n rho of t is exponential h rho t over h rho t times 1 plus something exponentially small. So this, we prove that we can get such estimates. I should say if rho is irreducible, although you can definitely remove this hypothesis by looking at semi-simplifications of all this. This is a comment that Kostas Tsouvalas told me. And it was also obtained independently by Cho and Sarkar by essentially trying to find finer properties of the codings of Samparino's flow. But our proof uses some results for some nice axiom A flows that also uses nicer properties of these codings anyway. So this essentially is, you can see this first prime orbit theorem as coming from mixing of the flow, and the second one here as being from exponential mixing, right? And exponential mixing is something which is not true for all axiom A flows, but it is true for some nice classes of axiom A flows. And one of the, what I mean by nice is that these stable and unstable distributions are very smooth. They come from something completely homogeneous here. And this is what gives you enough additional things to prove such results. And I'll stop here for now.
Questions? So you were saying that in this case, this constant C can be controlled by the exponential mixing constants?
Yeah.
What was the question?
The question was if this constant C is controlled by the exponential mixing constant.
How about the other way? Can you say something about the exponential?
Sorry?
Can you say what the exponential mixing rate is?
No, that's our next project. Is if we can actually control this exponential mixing rate geometrically from this representation.
I have a question I should have asked at the end of the first.
Okay.
But what is an instance where the closure of the periodic orbits is smaller than the non-wandering? It feels like in negative curvature. Maybe.
Yeah, if you just look at geodesic flows, you won't find any counterexamples there. I'm trying to remember. I've probably seen some examples of this when I was learning dynamics, but I don't know. Frédéric, you taught a dynamics class not so long ago.
It was last semester.
Oh, it was a long time ago then.
Negative curvature.
Yeah, I know, but so do I. So, yeah, I don't have an example right at the top of my head, but if you want to think about it, well, we can do that later.
Other questions? If not, thank Daniel again.